Welcome back. So now we are going to talk about minimum spanning trees. All right. So what are minimum spanning trees? So these are a concept that work for undirected graphs. So let's take an example. And because the graph is undirected, I'm not going to draw directions for the edges. Okay. Now the edges in this graph are going to have weights. So these are weighted undirected graphs. So 3, 1, 2, 4, 6, 5. Let's have some weights. Now what do these weights mean? So these could be an example. These could be servers in a network. And the weights could be link traversal times or delays. All right. So this is an example of a weighted undirected graph. So we'll assume each of the links is a two-way link. So each channel can transmit packets on both sides from 1 to 2, from 2 to 1. And 3 is the measure of the time delay it takes to go from 1 to 2 or takes to go from 2 to 3 and so on. And this could be an example of warehouses, and the weights could be transportation costs between warehouses. All right, so these are examples of graphs where there are weights. All right. Now what is a minimum spanning tree? So often enough when you build a network like this, we build a network with more links than are strictly necessary. So we may even add one more link here, and let's say the cost is 10. Okay. Now, so one of the problems is, suppose I wanted to route packets from, let's say, 1 to 6. So I wanted to route packets from 1 to 6. Well, there are many possible ways to route a packet from 1 to 6. So I could go from 1 to 2 to 3 to 6. I could go from 1 to 2 to 4 to 3 to 6. I could go from 1 to 5 to 6. So there are many ways of routing a packet. So a standard algorithm is, if 2 is a switch here, okay, now 2 has 4 ports that are coming in, right? So there are 4, 1, 2, 3, 4 ports at 2. So let's say a packet comes in from 1. One of the strategies that 2 could use is a strategy that's known as flooding. So what it could simply do is, whatever message comes in from 1, it could simply broadcast it on all the 3 ports. So it's going to reach 3, it's going to reach 4, and it's going to reach 5. It's not going to send it back to 1 because, let's say, it's intelligent enough to know that I'm not going to send it back to you if a message came from you, but I'm going to send it to everyone else. And this is called flooding, broadcasting. In sometimes it's called gossiping, even though that's slightly different terminology, so we won't use that terminology too much. It's called flooding, broadcasting, and so on. Okay, so this is an example of a routing algorithm. So if something comes in from one of the ports, I will just send it to every other port which it's not coming from. So when a packet comes, message comes from 1 to 2, 2 is going to send it to 3, 4, and 5. Now what about 3? Well, a message came in from 3, so it's going to send it to 6. And let's say 6 is the destination, so the message reached the destination. But it's also going to send it to 4. 4 is also going to send it to 2. 2 is also going to send it to 1. So as you can see, because of these cycles, flooding is going to be bad because it's going to keep resending the message over and over again. It's like it's going to keep circulating. And 6 is going to get the message from so many sources that it's going to get confused. So flooding takes a lot of work. So flooding means lots of lost bandwidth because I'm sending useless message over and over again because of cycles in my network, okay? Excuse me. And furthermore, because there are multiple ways to reach 6, 6 is going to get the same message 3 times, which is another way bandwidth is wasted. So bandwidth is wasted because of two things. One is there are cycles, and second is there are multiple ways by which I can get from a given source to a given destination. So how do we solve this problem? On the other hand, why would we like to do flooding? Well, the reason we would like to do flooding is it's brain dead. Okay, the algorithm is super simple, and internet switches, believe it or not, they are processing a lot of traffic volume. So a lot of traffic is coming to me, especially if I'm in the core of the internet. A lot of traffic is coming to me if I'm Verizon, and I need to route it quickly. I can't be making a decision every time. Oh, Sriram wants to send a packet to Google. Let me send it through this port. If I start making this decision every single time, life is going to be difficult. So I want to make simple decisions, and I want to make it fast. All right. If I wanted to do that, then how do I move about this process, right? So here's how I do it. All right. So what I do is I'm going to construct out of this network, I'm going to remove some edges. Or said in the positive, retain some edges. I'm going to retain some of the links, and I'm going to retire or temporarily retire some of these links. So for example, I could take 1 to 2, that's a necessary link. I could take 2 to 3. I could take 3 to 6, and then I could take 2 to 4. Then I could take 2 to 5. So here I am retaining some of these edges. I'm retaining 1 to 2, I'm retaining 2 to 3, I'm retaining 3 to 6, I'm retaining 2 to 4, I'm retaining 2 to 5. Okay, so retain, instead of some, let me say enough edges such that number one, the resulting graph has to be acyclic. I should not make a cycle up in the graph. So no cycles in this graph. And number two, it is fully connected. Strongly connected. What does it mean? There is a route from 1 to 6. There is a route from 6 to 1. There is a route from 4 to 1. There is a route from 1 to 4. There is a route from 5 to 2, 2 to 5, 5 to 3, 3 to 5. So every node is reachable to every other node. And what is the name of a graph that's acyclic and strongly connected? Well, that's a tree. So I want to retain enough edges to create a tree, and such a tree has a name. It's called a spanning tree. All right. So now we are encountered the concept of a spanning tree. So what is a spanning tree? A spanning tree is a subset of edges First of all, it's a subset of edges. So let me call it the subset of edges, S, subset of E. So it's a subset of edges such that the graph of vertices with the edges S is a tree. Okay, so it's strongly connected and acyclic. That makes it a tree. All right. So first of all, a spanning tree can only be built if your original graph is itself a strongly connected graph, which means you cannot have islands in your graph that are separate from the rest of the graph. So assuming that your original graph is strongly connected, I want to find a spanning tree. Not only that, I want to find a spanning tree which is minimum or minimal. So a minimal spanning tree is a spanning tree such that the sum of the edge weights is as small as possible. So among all the spanning trees, find me one spanning tree that minimizes the sum of the weights of the edges. So for example, here is the spanning tree. What is the sum of the weights of the edges? Okay, so 3 plus 1 plus 4 plus 2 plus 6. So 17. Let's take an example of another spanning tree. So we can go from 1 to 2 to 5 to 6. From 6 we can go to 3 and from 3 we can go to 4. So this is another example of a spanning tree of the same graph. And what are the edge weights? 3 plus 6, 9 plus 10, 19 plus 4, 23 plus 5, 28. So I would prefer this spanning tree here over the other spanning tree that I have shown. So given a graph G, given an undirected graph G, also fully connected or strongly connected undirected graph G. So our undirected graph is weighted, strongly connected undirected graph G like this. I want to find a minimal spanning tree, a spanning tree of the graph whose sum of edge weights is as small as possible. Now imagine if I found such a spanning tree. Well, this is going to be my routing tree. So such a tree can become my routing tree. What does it mean? So if a packet comes from 1 to 2, okay, if a packet comes from 1 to 2 and the destination of this packet is to 6, well, there is no need to flood anymore because it's a spanning tree. I know that there is exactly one port that I can send out to reach 6. I know that I can reach 6 by going out to 3. Okay, and so what each node does is build something called a routing table. It builds something called a routing table. So the routing table says if my destination is 6, send the packet immediately to 3. If my destination is 5, send it to 5. If my destination is 4, send it to 4. So now I can build this routing table, and this routing table tells me if a packet comes in from 1, destination is 6, I know exactly where to send it to. If the destination is 5, I know. So there is exactly one for every destination, there is exactly one outgoing edge that I can send things out to. Okay, so if it comes from 3 with a destination, so if it comes from 6, for example, to 3 with a destination of 5, 3's routing table is going to tell it to send it to 2. All right, so there is no more need for flooding. There is no more need for flooding. Number one. Number two, even if I flooded the network, what you will see is that first of all, that flooded message is not going to persist. So even if I were dumb enough to flood the network, okay, I didn't want to keep this routing table business, I don't want to flood the network, I'll still flood the network. So I flood a message from 1 to 2, I broadcast it to all the descendants of 2 along the spanning tree. Well, that's going to reach 5, it's going to reach 4, it's going to reach 3. 3 is going to send it further to 6, but 4 is not going to send it further because I don't send it on the incoming link, I don't send it back. So I'm not going to send it further. So if you notice, even if I decided to broadcast, the message is going to traverse and reach every node and traverse every edge exactly once, which is beautiful. Even if I decided to flood, I'm going to take a hit, but it's not going to be as bad as flooding the original network. All right. So now you can start to begin to see why minimal spanning tree routing is a very, very important concept, because if I route along this minimum spanning tree, and let me say that for every source destination pairs are equally likely for me, then in the end I end up with the best possible average time. So on the average, I will end up paying the least amount of time possible, because time here is money. So if I had warehouse locations and these were transportation costs, and there was equal amount of traffic from all the warehouses to all the other warehouses, like let's say it's equally traversed. If I shipped my goods along these spanning tree edges, then I will find myself having to pay the minimum transportation cost overall. So this gives me, computing the spanning tree gives me a strategy for sending traffic. So I will never send a traffic from 5 to 6. I would never send, those edges are retired. I would never send the traffic from 3 to 4. I would only try to send the traffic along the spanning tree edges. Now you may imagine, why do people bother sending 5 to 6 and 3 to 4? Well, often links go down. Roads have problems. Roads have traffic congestion. Internet links can go down. And if they go down, then what I will do is I will try and revive these links that are backup. So if this link goes down, then I will revive the 3 to 4 link. So Is this really being used in the internet? Yes. So spanning tree routing is an example of an algorithm that's actually used in the internet. It's slightly more sophisticated because it's done in a distributed fashion across all the nodes of the network, but still it's a very, very important algorithm. And so spanning trees tend to be super important, and we will have to study algorithms that, given a graph, computes the minimum spanning tree, minimum weight spanning tree of the graph. All right, so we will look at this algorithm coming right up. Okay, so now we are going to look at algorithms for minimum spanning trees. By the way, I shouldn't call it minimum spanning tree. Typically, it's called minimal spanning tree. In mathematics, minimal acknowledges that there could be many spanning trees with the same weights, and each of them is equally acceptable. Minimum typically implies that there is exactly one that achieves the minimum. It's a very technical point. Just read minimal spanning tree whenever I say minimum. All right, let's look at an example. And first, before we go into the algorithms, there are two very interesting algorithms. One is an algorithm by Prim. It's called Prim's algorithm. Another is a very interesting algorithm as well. It's an algorithm by Kruskal, Kruskal's algorithm. Both are equally interesting algorithms, and they are both greedy. So this is an poster child for greedy algorithms, and they are both based on very similar principle. They just exploit it differently. So let us first talk about this principle and then talk about how do the two algorithms exploit it separately for each algorithm. All right, let's take an example. So let's take an example. All right, let me put some weights. All right, and let us figure out that we have a minimum spanning tree. All right, and let me color the edges in the minimum spanning tree with pink. Okay, every non-minimum spanning tree edge will still remain green. Okay, so let me actually color it in pink without, so 1 to 2 is going to be part of it. Let's say 1 to 3. All right, 2 to 4. All right, 4 to 5. All right, and then 4 to 7 and 6 to 7. The other edges are not going to be part of it, so I'm going to make them dashed. Hopefully you can still see them. So that's going to be the minimum spanning tree. The edges that are not going to be part of the minimum spanning tree are 2 to 3, 2 to 5, 5 to 6. All right. So I claim that the edges that I have shown, oh, by the way, 3 to 4 is also not part of the MST. All right. So the MST itself is, let me redraw it again. It's going to have 1. It's going to have 3. It's going to have 2, 4, 5, 7, and 6, and the total weight is going to be 1 plus 1, 2, 2 plus 1, 3, 3 plus 1, 4, 4 plus 2, 6, 6 plus 1, 7. So I claim this is the minimum spanning tree. Now there is a very, very simple principle. So there is a simple principle to know when a spanning tree is minimum. So if I take any of these edges that did not make it, okay, so number 1, take an edge that did not make it. So take an edge that's not in T, that's not in T. So for example, let's take the edge 2 to 5. Its weight is 3. temporarily add it to the tree. So take any edge that's not added to the tree. So suppose I added 2 to 5 to the tree, it's no longer a tree, right? The reason it's no longer a tree is it now has a cycle. What's that cycle? The cycle is 2, 4, 5 and then the extra edge 2 to 5. So it's going to have a cycle. Well, in fact, it's going to have exactly one cycle. The cycle is going to be from 2 to 5, right? Now, all the edges in T along the cycle must have weight less than or equal to, so let's call this edge E the weight of E. So which means that if I added 2 to 5, its weight is 3. Now let me look at the edges along the cycle that are already in the tree, 2 to 4, 4 to 5. Well, those must have weights that are less than 3. Okay, that is the principle. So take any edge that's not in the tree. So let us take another edge, 2 to 3. Its weight is 2. Let us take from 2 to 3, let us take all the edges that are in the tree. So those weights are 1 and 1. 1 is less than 2, 1 is less than 2. Let us take 5 to 6. Its weight is 3. Let us take the path from 5 to 6 along the tree. Its weights are 1 less than 3, 2 less than 3, 1 less than 3. So this is the principle. So any MST, any minimum spanning tree must satisfy this property, this principle, and if it satisfies the principle, it is in fact a minimum spanning tree. Okay, it's an if and only if condition. Now why is that the case? Let us, for example, imagine there was an edge here from 1 to 6, like a giant shortcut, whose weight, let us say, was, I don't know, 1. So suppose there was an edge from 1 to 6 whose weight was 1. But let us say this minimum spanning tree did not consider this edge, right? It did not consider this edge. So it considered, so suppose I traverse from 1 to 6. So 1, weight is 1, so far so good, less than or equal to. Now if I look at 2 to 7, its weight is 2, and 7 to 6, its weight is 1. So I could do a surgery to the spanning tree. So what is the surgery I do? Well, let me take this offending edge, whose weight is actually greater than the weight of this edge that was left out. Let me delete it, let me take it out of the spanning tree, and instead add this new edge from 1 to 6. If I did that, then I still get a spanning tree. So if I take T union this E, but if I remove this edge F such that the weight of F was greater than weight of E, then the overall sum of the weights will have to decrease, right? So I have taken an edge of weight 2 in the original tree out. I took it out and I replaced it with an edge of weight 1. So the entire weight of the tree has to go down from 7 to 6. So this is not going to be possible in the minimum spanning tree. If you already claimed it's the minimum weight spanning tree, sum of the edge weights is minimum, I should not be able to take an edge out, add a new edge in, keep it a spanning tree, and reduce the weight all at the same time. Take an edge out, add a new edge in, maintain a spanning tree, all at the same time while decreasing the weight. Should not be possible. And therefore, if you found a true minimum spanning tree, it has to satisfy the principle. And what is this all-important principle? This all-important principle is the following. If you take any edge E that's outside, so I'm fixing the example back. If you take any edge E that's not in the spanning tree, take an edge E not in the spanning tree but in the original graph. In the original graph but not in the spanning tree, temporarily add this edge to the tree, okay? If you temporarily add this edge to the tree, so this edge is no longer there, okay? So I took it away. But take any edge that was originally in the graph, like the edge from 3 to 4, temporarily add it to the tree, consider it adding it to the tree, it creates a cycle. Traverse the cycle along the tree. all the edges in the tree that were along the cycle must have weight which is less than this new edge that you're trying to add. So if this new edge has weight 2, these edges have weight 1, then that's okay. And this must hold for every edge not in the tree. Okay, and if your tree satisfies this important property, then it is a minimum spanning tree. All right, and the proof is by contradiction. All right, if that much is clear, then we are now ready to look at two algorithms, Prim's algorithm and Kruskal's algorithm, starting with Prim's algorithm, that are going to exploit this principle to make up a spanning tree. Hopefully this principle is clear. If it's not clear, plenty of examples should be taken up and you should verify this principle. Take an edge not in the tree, look at the path from one of the points in the edge to the other end point in the edge, or look at the cycle that's created when you add it back to the tree and traverse that cycle along the tree. Then the nodes, edges that are already in the tree must have less weight than the new edge you are proposing to add. If that is indeed the case, then you have a minimum spanning tree. All right, very good. Okay, I will see you in the next lecture where we are going to talk about Prim's algorithm.